Hi and welcome to Gaffy's Grinds. This is video 6 in our series on thermochemistry. In our previous video, we learned about Hess's Law, where we looked at the theory behind that law. And today we're going to look at some of the calculations. So really we learned a theory in the previous video to build up to understanding what we're doing in the calculations. I could have just blindly taught you how to do the calculations, but I think it's going to make it mean more to you, and it's going to make it stick with you for longer if you actually understand what's going on. Before we jump in, we're just going to remind ourselves of a couple of things, and we're going to do that by doing practice. There's no point in me telling you again, so I have a couple of questions for you to do in a second. Before I do, the same things I always say, guys, try and eliminate any distractions now by closing any open tabs and stick your phone on silent at the very least. Even better, do not disturb mode, or turn it off or stick it somewhere else altogether out in another room. The other thing is all the tasks I'm going to give you to do, it's vitally important that you do them. If you don't do them, you're just not going to learn anything. I can't go and make you do them, but you're spending your time watching the video. You may as well actually learn while you're here. Okay, so a couple of questions. Some of this is recall. It's going to be retrieval of previous information, but there's a reason why this information is here. It's directly related to what we're doing today. So all the time we're building skills. We've been building up to this basically the whole way through the thermochemistry chapter. We've been building up to these calculations. So all the skills you've learned along the way are going to be applied now, and I just want to make sure that we're strong on them. So let's have a go at questions 1, 2, and 3. What? I'm missing a question there. Hold on just 1 second now. Pause the video. Apologies. That should be fixed now. So you have 4 questions there, and what I want you to do is I want you to get a piece of paper or a copy where you normally do these questions, and I want you to pause the video and try them, please. Okay, all right, so we're just going to go through them now. First of all, write an equation for the heat of formation of carbon dioxide, given that, well, you didn't need that. Just write an equation for the heat of formation of carbon dioxide. So you should have heat of formation of carbon dioxide. Okay, so we're forming carbon dioxide. So let's make sure we're forming carbon dioxide. So CO2 is carbon dioxide, and we are forming it. And when we're writing a heat of formation equation, we always make 1 mole of the product. So we have to make sure that the CO2 has a 1 in front of it, which it does at the moment. Okay. To make CO2, we're going to combine the elements carbon plus oxygen. So if you think back to the definition of what do we mean by heat of formation, it's the energy change when a substance is formed from its elements. So when 1 mole of a substance is formed from its elements, that's the definition for the heat of formation. That's why we have 1 mole of CO2 here, and we're forming it from its elements, which are carbon and oxygen. Now, obviously, this will have a delta H number, and I didn't supply you with that number, so we don't actually know the number, which that wasn't important there. I just want to see that you can write that equation. So if you got that right, tick it, and well done. Now, write an equation for the combustion of butane. Okay, so the combustion of butane. So if you didn't already have this done, and I hope that you did, you have to think about what happens during combustion. So the definition for heat of combustion is the energy change when 1 mole of a substance, so make sure it's 1 mole of the substance being burned. So remember, this is combustion. When 1 mole of a substance is burned completely in excess oxygen to produce carbon dioxide and water vapor. So make sure you've got oxygen, and then you've got carbon dioxide and water vapor being produced. If you didn't already have that, pause the video, do it now. Okay, so here we go. And guys, I'm a bit disappointed now at this stage if you can't do this. So you really should be able to do this. Like I said, if you're jumping in here and you haven't done any of the rest of the videos, then this is not a good idea. You need to go back and watch them in order. If you've watched them in order, then this should have been pretty easy. So butane is C4H10 plus oxygen is O2. Now, if you didn't know butane was C4H10, again, you should have if you watched our series on fuels, which you should have done before this. But if you didn't know that, and now you do, I want you to stop the video and finish that now. Make sure it's a balanced equation. Pause the video and finish that. Okay, this is what you should have. We're producing always the same products when we combust the carbon fuel, and that is CO2 plus H2O. And obviously, this is going to have a delta H equal to some number. Now, a little trick here is to know that this is going to be a negative number. We don't know what the number is at the moment because I haven't told you. Say the number is X. It's definitely going to be a minus number because it's a combustion. So it's going to always give out heat. When we combust things, we release heat. Now, let's make sure that this is balanced. That's the only other thing to check here. Make sure it's balanced. I'm going to show the balance and numbers in red. So here I've got 4 carbons on the left and I've only got 1 on the right. So I'm going to put a 4 to balance it. And again, if you're not sure how to balance an equation, there is a video for that too. You should go and watch that. It's an absolute basic skill. Okay. Right. Next thing I'm going to do is check the hydrogens. Why am I checking the hydrogens next? I'm going to leave the oxygens to the end because they're by themselves and they're the easiest to fix. So let's do the hydrogens next. 5 hydrogens on the left. Oh, sorry, 10 hydrogens on the left, 10, and only 2 on the right. So I can make this 10 by putting a 5 in front. That's 5 times 2 is 10. So now I'm going to do my oxygens last. I've got 4 times 2 oxygens here, which is 8. And then I've got 5 times 1 here, which is 5. So that's 13 altogether. I've got 6 on the right, so I can balance that by putting this as a 6.5 or 6.5. Well done if you got that right. Define Hess's law. Okay, well, what does Hess's law state? Hess's law states that the energy change for a reaction, this was just in the last video, the energy change is independent, so it does not depend, independent of the pathway taken. So it doesn't matter if it happens in 1 step, 2 steps, 3 steps, doesn't matter. The energy change overall will always be the same. So Hess's law states that energy change is independent of the pathway taken in the reaction. The last thing, and this is a really important skill, is to be able to identify the products and the reactants in an equation. So I'm hoping that you guys said that this here, the mercury oxide, HGO, is a reactant. I know this because it's on the left-hand side of the arrow. So left are the reactants. That means these 2 things are products. So mercury and oxygen are products. And I know this because they are on the right and they are produced. Again, very basic skill to know that stuff, and I'm hoping that you guys did know that. A couple more things that I need to make clear before we begin. One of those is, before we begin any calculations, one of those is we know that when we break bonds, for example, if I break this bond here, I've got C double bond O. If I was to break that, actually I've got C double bond O, double bond O. Here I've got some chemical bonds. If I was to break this into its separate elements, a carbon atom and 2 oxygen atoms chemically combined like this, if I was to break that into those things, I would have to break them bonds, and that would require energy, or it would involve an energy change. Okay. But one thing we must know is, say I have, for example, H bonded with another H. This is an element. Hydrogen bonded with another hydrogen is an element. If I was to break this bond, that would be energy in. So that would require energy. But there's only hydrogen present. And because this is an element, when those hydrogen atoms rejoin to make hydrogen again, that gives energy out to the surroundings. Now, because it's the same bond I'm breaking and I'm making, I'm breaking a hydrogen-hydrogen bond, and I'm making a hydrogen-hydrogen bond. These amounts of energy are equal. So to produce an element from itself, there's no overall energy change. Whereas to break a compound and then make a new compound, there can be an energy change because you're breaking bonds in the first compound and then you're making a new compound which has loads of different bonds. It's not the same bond like it is in this one. So that's an important idea, that to make an element from itself, there's no energy change. Whereas to make a new compound from an old set of compounds, that's when you get an energy change. One other thing I want to help you recall before we begin, and I know this is a lot of stuff, but I just want to make sure you've got this solid in your mind, is you remember back to video, I'm not sure what video it was, I think it was video number 3. We looked at energy reaction profiles. We did this by drawing a graph like this, where we had an X and a Y axis, and our X axis showed us the reaction progress. So we had reaction progress on the X, progress, and we had heat energy on the y-axis. Heat energy like this. And we said that some reactions start where the reactants are storing a lot of energy in their chemical store. So the reactants have a lot of energy. The reaction happens, and then towards the end of the reaction, we formed the products. But the products have a lower amount of energy, products. Now, in between, we have this thing, which is this arch. And this arch is what we refer to. Well, obviously, you can see that the energy increases. So the energy increases before the reaction can form the products. So this little increase in energy here, this here is known as what we call the EA, which stands for activation energy. And this is the energy that must be put in. Energy in. So this energy comes from the surroundings to break the bonds in the reactants and make them loose elements free to react, or loose atoms free to react. And then, in this case, the new product is formed and energy gets released. So from here, this amount of energy down to the energy that the products are storing, this here, the blue arrow shows energy out. Now, as you can see, this energy here and this amount of the energy out, these balance each other out. But all of this amount of energy below here, this extra energy that's given out, this will be the overall change in energy for the reaction. And you will feel, if you're anywhere near this reaction, if you touch it or if you put a thermometer into it, you will be able to detect this energy has been given out. And I told you at the time that we can measure this energy change, or we can consider this energy change. And I told you we were going to come back to this. So we're going to say the energy change overall is equal to the energy out. And of course, the energy out happens when the products are made. So when the products are formed. And if we take away the energy in, and of course, that's when the reactants, the energy of the reactants, by doing that sum, energy out, take away energy in, we can get the total energy change for the reaction. That was what I told you in video 3. Now I'm going to make that just a little bit more complicated here, and I'm going to use the symbols instead. So we've got delta H. Delta H just means change in heat. So delta H for the reaction is equal to, I'm going to talk about this symbol here. It's like an E, like a capital E, but it's a bit skewed. And what this means is sum of, as in when you do a sum, you add things up, okay? So it's the sum of the heat, delta H, and a little f, which stands for formation. So delta H of formation for the products. So this is just replacing this up here, energy out. So the energy out is just delta H of formation of all the products, the sum of that. Take away delta H of formation of the reactants, which is the same thing as the energy in. So the delta H of formation of the products is equal to the energy out. Delta H of formation of the reactants is equal to energy in. So I'm just going to highlight those to make them match. So delta H, or delta H of formation, delta HF of the reactants is equal to the energy in of the reactants. Different color. Delta H of formation of the products is equal to the energy out of the products. And lastly, the delta H of the reaction is the same thing as saying the energy change for the reaction. Okay, so those match up. Now what I want you to do, and again, this is going to make more sense. I'm going to ask you to stick with me, and this is going to make more sense once we actually do some practice examples. So I'm going to get you guys just to pause the video and take down that equation now. It's going to be important. Okay, so you should only be watching the video if you've taken down the equation. Now for the next bit of the video, I'm going to just get a blank screen over here. You are going to need a couple of things. Okay, the first thing that you're going to need is you are going to need to get a calculator. So we're going to be doing some calculations, and you're going to need the sheet. The sheet is basically a Microsoft Word document with the questions from this video on it. Now, what I want you to do is either, if you have a tablet that you can highlight things on Word. So if you've got a tablet and a stylus, or even a tablet and your finger, and you can highlight on Word, then that will do fine. Okay, you can just open up the Word document that's linked in this video below, and you can open it up on your tablet and do it like I'm doing on my tablet. If not, then I suggest that you print off the sheet, because it's really important that you have, I'm going to be showing you some skills of doing these questions. And it's really important that you've got a copy of the questions that you can highlight, because I'm going to be getting you to highlight different parts. If you really can't do anything else, and you don't have a printer, you don't have a printer, and you don't have a tablet, then the only other suggestion I can make is that you write them down word for word, exactly the way they are on the screen on paper. Now that's long and laborious, but unfortunately, for this to work properly the way I'm going to show you, I need you to be doing exactly what I'm doing. Okay, so go get the things you need to get now. Pause the video, go get them. If you can, print out the sheet, and if you can't, get it up on your tablet at least. Other than that, you're going to have to write it down word for word. Okay, so go do that now, please. Okay, here is the first question. This is typically what they look like. This is the question. It's question 6C from 2019. Okay, and I'm going to show you how I would approach this question. The first thing I'm going to have is I'm going to have a selection of highlighters, and I'm going to read my question. Okay, I'm going to really read and study my question. They typically all tend to look like this. You get an equation. They give you the names of the chemicals, and they give you some numbers, some values for heat. Okay, and they ask you to calculate something. Okay, now the first thing that I'm going to do is I am going to match up the chemicals in the equation with the chemicals and the names of things that they give you. And I'm going to use a different highlighter for each one. So let's have a quick read here. It says tetraethyl lead burns completely according to this equation. So tetraethyl lead burns quickly according to this equation. So we've got this full balanced equation. Now, it says underneath, the heats of formation of tetraethyl lead, carbon dioxide, water, and lead oxide are, and you get 4 numbers respectively. Calculate the heat of reaction for the combustion of 1 mole. That's really important. 1 mole. Heat of combustion is always 1 mole. Now, that's why we practice writing those out, because we have to always have 1 mole of tetraethyl lead. Now, note here in the equation, what have I got? I have got, this is tetraethyl lead, and I've got 2 moles of it. So straight away, that's setting alarm bells off for me. Okay, now, as you can see, I've highlighted tetraethyl lead. Now, you may have never come across that compound before. You probably should have because it comes up in fuels, but even if you haven't come across that, you can figure out which one it is by process of elimination, okay? Now, I've chosen yellow for tetraethyl lead. So every time I see tetraethyl lead, I'm going to highlight it yellow. Now, this is the most common mistake I see students making on these questions, is they mix up which formula belongs with which name and belongs with which number. That's literally the biggest mistake people make. So tetraethyl lead is this one, and here's its name. The heats of formation of tetraethyl lead. Now, it's the first name here. It says the heats of formation of tetraethyl lead. Where you have the first name, that means the first number for the heat of reaction is going to belong to tetraethyl lead. So the first number here is 52.7, like that. So 52.7 is the number that belongs to tetraethyl lead. In a different highlighter now, I'm going to do the next name. So the heat of formation of carbon dioxide is here. Let's find carbon dioxide in the equation. There it is in green. So I'm going to keep the same color system. And it's the second name in the list, which means it's going to be the second number here. You're getting the picture. That's what we're doing. Okay, let's go pink next. The next substance is water. H2O is the equation for water. And the number I've got here is minus 285.8. Last color, I'm going kind of a pinky, and it's going to be lead 2 oxide, and that's going to be the fourth number, minus 219 kilojoules per mole, and it's this here, PbO, lead oxide. Pb is lead, O is oxide. Now, like I said, tetraethyl lead there is a difficult one. It's something you're not going to come across very often. But by doing the other three, carbon dioxide, water, and lead oxide, you should know them ones, then you can figure out by process of elimination that this first one that I've highlighted in yellow must be tetraethyl lead. Okay, now what I'm going to do is I am going to start the second one for you. This is why I'm hoping that you have, we're not going to do any of the calculation yet. We're just going to practice picking out the numbers like I have there. I'm going to start it, and when I've said it, I suggest you print these out so you can do the same thing. If not, you do them on a tablet, and if not, then the worst case scenario, you have to write this down exactly the way it is, word for word, and then highlight it. And that's going to take longer, but if you've got no other way of doing it, you're going to have to do that. Okay, right. Here is how we do it. So calculate heat of combustion of methane thiol, which is methane thiol according to this equation. So you get the equation. Now, methane thiol has to be this one here because it's the only one that looks different than stuff I'm used to seeing. I've got carbon dioxide, water, sulfur dioxide. I know all of them. So this first one must be this methane thiol here. So the heats of formation of methane thiol, it's the first name in the list, and therefore it must be the first number, like that. Okay, so what I want you to do is I want you to pause the video and I want you to do the next three for me. Okay, so you should only be watching the video if you have highlighted the names, the formulas, and the numbers in for each of the compounds in this equation. So the next one I'm doing in green is carbon dioxide. The name is here. It's the second name in the list. So it's the second number in the list. It really is that easy. Different color. I'm going with an orange here. Water, H2O, is the third name in the list. So it's the third number in the list. And last color is lilac-y color. It's got to be this one, which is sulfur dioxide. If you didn't know the name, well, it's written right here, sulfur dioxide, and the number has to be minus 296.8. It really is that easy, and this is the hardest part of this question, really. Right, this is the next one. I'm going to get you to do this one all by yourself. Okay, it's a little bit harder, but you should be able to manage it. So pause the video and do this one by yourself now on either your paper or write it down word for word. The way it is there. Okay, so you should only be watching the video if you have completed the what I've asked you to do. Notice here, there's Hess's Law. So they're asking you for that definition that we learned in the previous video and we practiced again today. So that would be marks in this question. Then it says the heats of formation of dodecane. So dodecane is the first name. So it's got to be the first number. Minus 350.9 is the first number, and that's going to be that one there. Now, if you're not sure, you can leave it. You're not sure which equation it is in the equation, you can leave it and eliminate the other ones. So this is butene. You should definitely know this from fuels. Butene is the second name, so it's got to be the second number, and there it is in the equation. I'm going for a green color next. 2-methylbutane, and again, you should definitely know this one. It's already given you to the name, not the formula in the equation. And there is the number. It's the third name, so it's got to be the third number. And last of all, a red color here. We've got X. We don't know what the name of X is, but it's here, and it's 20. Okay, well done if you got that right. And the last one on the page here. I want to pause the video and do this one for me, please. You should have this. Sorry, this should be number 4 on your page, and it's 2017. Question 6. I'm not sure what part it is, but pause the video now. Okay, so you should be playing the video if you have finished that again. So let's check this out. So calculate the heat of reaction for the conversion of octane to ethyl benzene, given that the heats of formation of octane. So octane is the first name, so it's the first number. And octane has 8 carbons, and it's an alkane, so it's going to have 18 hydrogens, and that's it there. Okay, second color I'm going for is green. The second thing is ethyl benzene is the second name, so it's the second number, and this has got to be ethyl benzene. Now, here's a little trick question. Why is there no heat of formation for hydrogen? Okay, so speak your answer to the screen. I did warn you about this earlier, so on 3, speak your answer to the screen. 1, 2, 3. I'm hoping he said something like this. There's no heat of formation for hydrogen because hydrogen is an element, and elements basically form from themselves. So you break the bonds between 2 H atoms, you make the same bond between 2 H atoms. It's the same energy in as the same energy out. So there's no energy change. So it can't have a delta H of minus something because there's no energy change. Okay. Right. So that is, I promise you, that actually is the hardest bit. If you can do that, I think you can do the rest. No problem. The next thing that we do is we apply the equation. So the delta H of the reaction is equal to the delta H of F, which is the delta H of formation. And I've missed something. I've missed this sign here. The sum of delta H of formation of the products. Take away the delta H of formation of the reactants. It's that simple. Okay, it really is that simple. The one thing we're going to watch in this equation is this guy here. It's a heat of combustion, so it has to be for 1 mole. Okay, it has to be for 1 mole. That's the big thing. So let's go to the next line. Now what I'm going to do is I'm going to directly apply. What I'm going to do is I'm going to divide the whole equation by 2 here, because I want to make this into a 1. And by making this into a 1, this becomes 13.5 oxygens. This becomes 8 CO2s. This becomes 10 H2Os, and this becomes 1 PBO. Okay. So I am applying that idea right here. I'm making sure I've only got 1 mole of the product that is being combusted. Now, you could do it all and then divide by 2 at the end, but I prefer for you to actually see what's going on here. I'm fixing the problem that I have. I need it to be 1 mole of the combustion product, or the combustion reactant. So that is this chemical here. I have to make that to a 1. By dividing by 2, I have to divide everything by 2. And then it's literally a matter of plugging the values into the formula. The first thing I have to do is get the sum of the delta H of formation of all of the products. Now, this is a skill we've built up already. What are the reactants and what are the products in this reaction? So pause the video now. Tell me, what are the products, please? 1, 2, 3. Speak your answer to the screen. I'm hoping you're saying carbon dioxide, CO2, H2O, and PBO, because they're all on the right. So what we're going to do is we're going to put in the delta H of formation for each one of these. But we also have to take in the molar quantities into account. So I'm going to do the CO2 first. I've got to put an 8 times the heat of reaction because there's 8 moles here. So 8 times, now carbon dioxide is minus 393.5. So 8 times minus 393.5. Now I'm adding to this because it's, remember, this is the sum of, this means sum of all the heats of reaction of the products, or all of the heats of formation, sorry, of the products. So 8 times minus 395.3, then I'm going to do plus 10 times, because water is 10 now, I've divided it by 2, remember? So it's 10 times, and the heat of formation of water is the pink one, or is the purpley one, it's minus 285.8, like that. Plus PBO is another product. I've only got 1 mole of PBO now because I've divided by 2. So plus 1 times, and it's just minus 200 and, no, am I wrong? Yeah, no, minus 219.0. So I'm going to sum all of those, but then I have to take away the heat of formation of the reactant. So the reactant in this equation, I've only got 1 reactant because remember, oxygen is an element and it doesn't have a heat change. So only the tetraethyl lead will have a delta H value. And the delta H value, so I'm taking away 50, oh, sorry, it's not minus, it's just 52, it's positive, 52.7. Like that. Now that's very messy. Apologies, I'm just going to fix that up a little bit. Not happy with that. So I'll just get my rubber and I'm just going to, yeah, okay. So we've got 52.7, like that. Okay, and I need to do that whole sum. So you need a calculator now. Absolutely 100% use your calculator. You're allowed to, so you should. And I'm going here to do, well, first of all, I'm going to do up the sum of the products. So I'm just going to do this bit first. Okay, and all of this fits into here. The sum of the delta H of the products. And then this guy is the sum of the delta H of the reactants. Now there's only 1 reactant here, so there's only 1 value here. So I need my calculator and I'm going to do that now. So I'm doing 8 times, and be careful using brackets here, make sure you use your brackets. 8 times minus 395.5 or 393.5 plus 10 times minus 285.8 plus minus 2. Oh, I've got an issue here. Plus 10 times, yeah, minus 219. So that gives me minus, oh, sorry, minus 6,225, which is the green. So that is this. And then I'm taking away, which this comes from this guy here. And I'm taking away 52.7, which comes from here. So when I do that, take away 52.7, that gives me equals, equals 6,277.7, and the units are kilojoules per mole. And this is the delta H for the reaction. That's your final answer. And the great thing about it is that all of these are the same. Okay, so the delta H of the reaction equals 6,277.7 kilojoules per mole. Okay, right. So I'm hoping that you've found that pretty easy to follow. A lot of people get scared of this particular calculation, but there's only a little bit of addition, a bit of multiplication. It's not really that difficult. In fact, like I said before, the biggest mistake I see people making is I see people getting the values wrong because they don't highlight the question like I've shown you. What I'm going to do is just get you to pause the video and take that down as an example. Okay, we're going to move on and we're going to do another one. Sorry, this video is going to be a bit long because I'm modeling how to do these equations. I'm going to help get you started on this one, and then I'm going to let you guys finish it, and then I'm going to give you a couple to do by yourselves. Okay, so let's try number 2. Now, first of all, let's see if you guys can recall what the equation is. Can you write down the equation that helps us figure out what is the heat, the delta H for the reaction? So I'll get you started. Got the delta H of the reaction. So without looking back now, I want you to pause the video, see if you can write down what the formula is to work this sum out. Okay, so you should only be watching the video if you've tried to write down the formula. This is it coming up here. You've got, don't forget the sign, sum of. That's probably the thing you forgot. I forgot it in the previous question. It can happen. Sum of, you should have delta H of formation. So delta H of formation, little f means formation. And in brackets of the products. And then you're taking away the sum of the delta H of formation of the reactants. That. Okay, so that's a good start. Right, the next bit, we're going to do sum of. Now, in this case, we don't have to worry about dividing anything by 2 because we've already got only 1 mole of the combustion reactant. It's already done. We don't need to worry about it. That equation is good the way it is. Okay. Now I'm after taking away that highlight. Sorry, there we go. Now, first of all, identify the products and the reactants. So what are the products in this reaction? Please speak your answer to the screen now. Okay, your products, I'm hoping you're saying, are carbon dioxide, CO2, water, H2O, and sulfur dioxide, SO2. We know this because it's on the right of the arrow. So let's put in the delta H values for the products because that's what we need to put here. Remember, we need the delta H values of the products. Now, carbon dioxide just has a 1 in front of it, so we just need minus 393.5 like that. There's no mole number in front of it. We don't have to multiply it by anything. And then we're going to sum it. So remember, this means sum, which is add. So we're going to add to it the delta H values for the other products. So pause the video and add in the delta H value for the other products now, please. So you should only be playing the video if you've added in the delta H values for the other products. I'm hoping that you spotted that the water has a 2 here, which means we have to multiply the delta H by 2. Now that can catch people out. And the water value is minus 285.8. And the great thing about the color coding is this is really easy to see now. I'm adding to it. I'm hoping that you remember to add in the delta H of formation of the SO2 because that's also a product. And that is minus 296.8. Like that. And all of that, we're going to sum that up. So we're going to add it up. So I'm going to put extra brackets around the edge to make sure all that is done in one sum. And that is the delta HF of the products. Now remember, we've got to take away, from here, we've got to take away the delta H value of the reactants. And that is going to be what we have in pink. So that is going to be minus 22.8. All right, you do your sum then, and go ahead and pause the video and do the sum, see what you get. Okay, so I'm hoping that you got a delta H for the reaction. You put it in your calculator, equal to minus 1239.1 kilojoules mole to the minus 1. So kilojoules for every mole. And what that basically means is for every 1 mole of this stuff that we burn, We release this much energy. Now, how do I know? Why am I saying we release it? How do I know it's released? So 1, 3, say your answer to the screen. 1, 2, 3. We know it's released because this is a negative delta H value, which means it's exothermic, so it's released. Okay, that's how we know. Now, if you did not get this number, but you have all of this the same as I have it, and you check it, make sure it's exactly the same. If you have all of that exactly the same, but you did not get this number, then you have a calculator error. You have put something in on the calculator, or you haven't used brackets incorrectly. So you need to check it again. Put it in exactly the way it is with all the brackets into the calculator. You should get this answer. This is the right answer. I've checked it. Okay, so there are two more questions on the sheet that I've linked in the below the video here. I want you to do them from scratch now. So we've done the highlighting. I would like you to do the delta H of reaction values the exact same way as we've done for those two now. If you don't have the questions printed off, they're written on the screen here. You can take them down. Make sure you take them down word for word, exactly the way they are, with the numbers and everything in the right order, and you highlight them and get started. So I want you to pause the video and do those now. Okay, so for these, I'm just going to put up the answers. Okay, so I'm not going to do them all because the video will go on too long. We've got a delta H here equal to, you should have 183.2 kilojoules per mole. Well done. If you got that right, you've done a really good job if you got that right. Notice that this is the first time we're seeing a delta H that is positive. Okay, so this is energy being taken in overall in this reaction. So that means it's what type of reaction? Say the word on 3. 1, 2, 3. The word is endothermic. It's an endothermic reaction. In the last one then, I'm going to give you the answer for it. The delta H of this reaction, delta H of reaction, is equal to 237.6. Is it? I can't really see what I've written here. Give me 1 second. I'll have to do this again. Give me one. Yeah, that would be that would be plus 237.6 kilojoules mole to the -1. Now, if you've got that right, guys, really well done. That is the last one I'm going to do in this video because the video is going to get very long otherwise. There's lots more to practice, guys. If you have exam papers, they will be in there. Sorry, I should have said they'd be in the exam papers as well. If you have printed exam papers, then you could have used them. That's stupid me. But anyway, if you have exam papers, or if you go to examinations.ie or study clicks or something like that, you can find a lot more of these to practice. But this method I've showed you works for all of them. That's the beautiful thing. I'm hoping that if you did 1 and 2 right with me, that you got number 3 and 4 correct there. If not, again, I would say it's just something small you're doing. Just double check everything, go back and check the way I've done it again, and you should be able to work it out. If you want me to do more, if you want me to do a second video with these calculations, please do leave a comment in the description, especially if you have any specific ones that you can't figure out from any year, and I can make a video showing you how to solve them. But the big thing is that you take away that you are able to do these calculations now. And like I said, if you need me to do more, we can arrange it. So just leave me a comment. If you can like the video as well, it might help other students who are struggling with this for some reason. People find this very difficult, but hopefully you can see there's not much to it once you get the hang of it. The hardest thing is actually highlighting the values and the names and the formulas and making sure you're matching up the right stuff. All right, that's it, guys. I'll see you in the next video.